Welcome back, Year 12s. In this video, I'm going to take you through the start of transition matrices. So this will actually form the next 3 lessons of our work. I'm going to take you through all the basics today, the formula that we can use for these as well, how to set them up in a matrix, how to interpret them, and then in a separate video, I'll show you binary transition matrices. So I'll get to those in a minute. You'll see them in your notes. We might skip over them with this video, but then you'll watch another one for me just for those 2 examples. So what we're going to be looking at are situations where you've got something moving or changing within a system. So when I'm talking about a system, I'm talking maybe about, you'll see in our example down here, we're talking about warehouses and trucks that are moving between warehouses. But you can also have like people rotating through like gym sessions. I've seen examples like that. People rotating through shops that they like to visit. We're going to be working a lot with percentages and obviously with matrices as well. So I might just get straight into it. So first of all, when we're looking at a transition matrix, they will be a square matrix. And a couple of really important notes is that when we look at the columns in a transitional matrix, they're going to always add up to 1. Now, this is particularly important because we're going to be constructing these a lot of the time, or you might have one missing element and you're going to have to fill it in. So you have to know what we want those columns to add up to. The reason we want them to add up to 1 is because we are going to be working with percentages, and so we're going to be working with 100% being encompassing everything. So that means that when we convert to a decimal, our percentages that is, and then we add them up, they're going to equal 1. So for example, here it says percentages are written as decimals, so anything that's 30% will convert to 0.3, and then of course all the other percentages when we add them in will total 1. So I'll start off with this one because it's fairly straightforward. You've got delivery trucks and they're transferring goods. We've got 2 warehouses, warehouse A and B. And what happens is that the trucks might start the day at a particular warehouse, but by the end of the day, they might be parked at a different warehouse. Some of them might stay at A, but some of them might move to B. And that's where the percentages are going to come in, because they're going to tell us how many or what percentage of the trucks will start at A and stay at A that night. What percentage then will go over to B? And then what about the ones that started at B? What percentage of them will stay at B? And how many will stay at A? And so we can summarize that in a table. You'll see down here it says a transition table. So basically here, it's a 2-way table. This value here is a decimal from that percentage, 70%, converting to 0.7. So it's saying from this warehouse, if they start there, 70% of them will then transition to warehouse A and so forth. So from B, 40% will come to A of the ones at B, 60% will stay at B. And from there, we can go straight into a matrix. But sometimes you'll actually be given a diagram instead. I might just zoom in a bit. Diagrams will demonstrate basically using a network. You have vertices labeled as we have here, warehouse A and warehouse B, and then you have loops demonstrating which things are staying at A, say starting at warehouse A and staying or returning that night, 70%, or starting at B, staying at B, 60%, and then you'll see what proportion or what percentage, because these could be written as percentages or as decimals, you'll see the movement, so it'll be shown with the arrows. So it is a directed network. What we want to be able to do is put it into a transition matrix. So what you're always going to do is make sure you've got your from, or your starting point is going to be written in these columns here. So A and B are our two warehouses in this example. And this, the rows, that's going to be, I might just write it on this side, I've got more space, our to or our finish point. So they might start at, say, A and then finish the day. So from finish the day at A, and we can see that 70%, that's written as 0.7, so 70 divided by 100, in other words. And that means that 30%, the rest of them, must be going to B. So not going anywhere else. We're talking about movement just between these two warehouses. And so that's why we can see that the column must add up to 1. You've got your 70 and your 30% giving us all of the trucks that started from A. If we have a look here, we've got 60% that start at B, end at B. So that's over here, down in the bottom right corner, 0.6, which means that this value up here has to be 0.4. But we can see from the diagram anyway that it's 0.4. That there is our first transition matrix. We've got a few examples underneath, of course, that we can use to just do a little practice. Again, we've got A and B. And if you do need to, you can always write your start and your finish, but we don't actually need those labels because it will always be start and finish, like so. We've got 32% or 0.32 start and finish at A, and then as you can see, we've got 68% that are going to B. We've got from B to B, 0.55, and B to A, 0.45. So there's another one there. What have we got down here? We've got 3 now, 3 different things in this system. So that means we're going to have a 3 by 3 matrix this time. Okay, so we have got, I like to do the loops first, but that's just me. A to A, 0.7. B to B, 0.9. So you'll see the loops going this leading diagonal. And C to C, 0.75. So the diagrams can get a little bit more confusing the more that you've got there. So we've got A to C, if you follow the direction of that arrow, is 0.1. And A to B is 0.2. And we should see that add up, 7, 8, 9, 10 to 1. So it does work. We've got B to A, so B to A, 0.1. And we've got B to C. Or do we have B to C? We don't. So notice there's no arrow there. And also, I know it's going to be 0 because this already adds up to 1, the 0.9 and the 0.1. So no B to C. What have we got over here? C goes to A, 0.25. But C does not go to B. There is no arrow that links C to B. And if you have a look here, 0.25 and 0.75 adds up to 1. And then finally, we've got this one, which has come from an exam. I'm going to just put them in sort of alphabetical order. Whoops. Oops, this is playing up a little bit, as you can see. There we go. And then I'll do the loops first, so A to A. L to L is 100%, which means 1. Now, because I've got 100%, I know that these will all be zeros. So I'm going to put them in straight away. O to O is 0.8. And P to P, 0.9. Oops, I've put that in the wrong spot. There we go, never immune to making a mistake. So 0.8 was O to O, should have gone down here along the leading diagonal. And P to P, 0.9. Oops. All right, then we just have to look at the other arrows that we've got here. We've got A to L, 0.2. A to O, 0.1. And then there's no A to P. O goes to L, 0.1. So line that up. Doesn't look like O goes to A, so 0. And that means that we've got 10% left over, O to P, 0.1. And finally, P to P we've done. We've got P then only going to L, P to L, 0.1. 0 and 0. There we go. So there's a little practice constructing the transition matrix. Now what we want to do is have a look at how we start to use them, interpret them and use them. So with this one here, it is the same think it might be, oh no, it's a different one. Same situation as before in that we've got a network and we're transferring that network into a transition matrix. So before I read the question, I might just get that information in. Actually, it's probably better practice to read it first. We've got 3 candidates in an election. So A, B, and C are representing these 3 candidates. So the actual transition that's happening here is the voters changing their preference from one of these candidates to another in those months leading up to that election. So this is a transition diagram is showing those percentage of voters that are changing their decision on the candidate that they like from month to month. So if we have a look here, A to A is 0.75. So 75% of the ones that prefer Miss Abood want to stay voting for her. Then we've got 80% for Mr. Broad are going to stay voting for him. And then we've got 40% for Mr. Choi are going to stay voting for him. All right, I'll just continue filling this in. Just a note about this one, this is 5% that are changing their vote from A to B. So this one just here. One of the most common mistakes that I see is students write 5% as 0.5. Oops, 0.5. Now that's incorrect. 0.5 is 50%. We know that's a half. So just be really careful with that because it's a very common error. 5% is 0.05. So what you should get looks like this. And then we can check that it adds up to 1. It does. Each column, adds up to 1. Okay, so just in terms of interpreting it, if we have a look at the next question, what percentage of voters who prefer Mr. Broad this month, so this month is along here, and down here we have next month. Always you're starting and you're finishing over here. Oops. Okay, so what percentage of the ones that prefer Mr. Broad, so we're looking at this column, are going to prefer Miss Abood next month? Looks like we're looking at this value, B to A. B to A is 10%, or as you can see, it's 0.1, so we're going to have to convert it into a percentage. For Mr. Broad, so that's B to B, we're looking at 80%. And then finally for Mr. Choi, so B to C, 10%. Now, what's going to happen is that we're working with percentages, obviously, in the transition matrix. However, we are going to be asked about values. So we're going to be asked to use the percentage with a total value to find how many people, so how many of these, rather than what percentage. So we are told that in January there are 6,000 people who preferred Miss Abood, so A in your matrix. So how many of these are going to change their preference to Mr. Broad? So we're saying how many are going from A to B? First, let's have a look at that percentage. So just up here, A to B is 5%. So just write that down. We've got 5% that are going A to B. So this means it's going to be 5%, so 5 over 100, of the ones, or the total, that preferred Miss Abood in that particular month. So in January, they said. So 5% of 6,000, you can do that in your calculator if you wish. So there we go, 300 people. So be careful of those sorts of questions. Generally, if they're telling you how many people altogether, that's a big clue that they're not asking you for the percentage, they're asking you to use that percentage. And in this last question, we are going to see well, we're going to see a calculation that we're going to have to make, but a calculation that's going to be made much easier by the matrix when we work further with these transition matrices. So we've got 6,000 people preferring Miss Abood in January, as before. We're also told, though, how many people prefer Mr. Broad and how many people prefer Mr. Choi. So from this information, how many people will prefer, it should be will, prefer Miss Abood next month. Okay, so let's just consider. We want the total next month, so in Feb, how many are voting for A, which represents Miss Abood. Now we have got groups of people in three different, preferring three different candidates, and we have percentages of this group, the 6,000, percentage of this group, the 3840, and a percentage of this group, the 2160, that are going to change their preference or keep their preference with Miss Abood. So we have to actually do three separate percentage calculations here and add them together. So the first one we're going to consider, if we're looking at how many people next month are going to prefer Miss Abood, we are really looking at, whoops, it's not going to allow me to use, oh yeah, there we go. We're really looking at this row because this row represents, have a look here, next month, and those that are changing their preference or keeping it for A. So we can see 75% of the ones that preferred Miss Abood before will like her again. 10% of the ones that preferred Mr. Broad will change to Miss Abood, and 20% of those who preferred Mr. Choi will change to Miss Abood. So we have to work with these three percentages here with the three values we were given. So first of all, 75% of the 6,000 people that were with A initially, they're going to stay with her. So 75% of 6,000. The next one was 10%. So 10% of this group of people, they were the ones that liked Mr. Broad last month or in January. They're going to switch, and we're going to add that to the 20% that switched to Miss Abood from Mr. Choi. So 75% of 6,000, 10% of 3,840, and 20% of 2,160. So you can do that in your calculator, and you should get 5316. So next month, Miss Abood will have 5,316 people that are going to get her vote. As you can see, that that calculation there was fairly tedious in that we had three separate things we had to identify, three different pieces of information, and we had to then do the percentage calculation and add it all together. Now, the thing is that, yes, we can do that, but what's actually much easier is transferring that into a matrix run and dive. So basically using this information here that we were given, the 6,000, the 3840, the 2160, putting that into a matrix, what we call a state matrix. And since these three values here represent the run of my run and dive, I can use those values in another matrix and use matrix multiplication to make this particular calculation a lot more efficient. So I might just skip over binary transition matrices for now. So if we just skip that, I'll come back to that in a separate video because I just want to show you how we can put this sort of information into a more efficient calculation, and that's really what we're going to be doing with these transition matrices. So if we're given information about values of our variables initially, so what are, like how many were for each candidate at the beginning, we can use that transition matrix to make predictions on any future value. So what we're going to do is create this, I mentioned it before, an initial state matrix, and we're going to give it this symbol S0. So this is for an initial state matrix. Now I'm going to use this example down here. to do this. We've got a survey that shows 75% of the time customers continue to purchase their groceries from store A if they purchase their groceries from store A the previous month. So I've got this month and I've got next month. So 75% will stay shopping with A. Let's get rid of that. While 25% of the time consumers will change to store B. And that adds up to 1. The other information we're told, 80% of the time consumers will continue from store B if they purchased from B the previous month. So 80% here. Notice they don't tell us B to A. We don't need to tell us B to A because we know that would have to be 20%. So 0.20. So it says create the transition matrix. We'll use a capital T for our transition matrices. So I'll label that one as capital T. Okay, this is where the state matrix is going to come into play. We're told that in January, we've got 300 customers that shop at store A. So state matrix is going to be a column matrix. You'll label it the same way that you label the columns in your transition matrix. So the ordering of the letters you put on the rows needs to match what you put on the rows in here, and on the columns as well. So I've got 300 shoppers at store A and I've got 300 shoppers initially at store B. So this here is our initial state matrix. It's what are the values at the beginning. So what we're told is to use this matrix and this state matrix to find the number of shoppers at each store in February. So what we can do is we can take our transition matrix. Now, since this one's called S0, that's for for Jan. So that means that we create our next state matrix. We call these state matrices, these ones that are labeled as with an S, and that's going to represent the values that are in February. So how many shoppers at each of the stores in February? And what we do is we take our transition matrix and we multiply it by the state matrix. So we basically are doing, I'll show you so it makes a little bit more sense. Doing this. And what we're going to see is that this row was for row A. So this was all the people transitioning to A. So 75% of 300 plus 20% of 300. So because we're doing this run and dive, we are automatically applying that percentage to the two values we were given. And because it's matrix multiplication, it's also going to add them together. So this is our much faster way of doing that calculation that we had earlier, this one at the bottom. This is our speedy shortcut way of using matrices to make that calculation much more efficient. When we do that in our calculator, we get 285 and we get 315. So in other words, after all these transitions have taken place, so we've got the 75% of this, the 20% of that, but then we've got this other transition taking place, so 25% of A moving to B and 80% of B remaining at B. These are the new values at each store, and of course this is for February. So I'll just say, therefore, 285 shoppers at store A. We probably should have said customer rather than shopper, but that's all right. And 315 at store B. So just put a final answer there. So now we've got values or where the shoppers are where the customers are shopping in February. Now this is why it says recursively find, because now if I want to find March, I have to use my previous values. I have to use the values for February and I have to transition those values. Because remember, that transition matrix is not just for January. It's saying in general, for any month, these are the transitions that happen month to month. So that means that what I can do for March, which is going to be S2, the very next month, I can take my transition and I apply that now to the February value, so the S1 matrix. Now that is going to look like, same as before. Now you don't always have to write this matrix out, by the way. It's much easier just to write T by S1. But I just want to show you now, obviously, what it looks like. It's now being multiplied by 285315. Since these initial values are no longer relevant because shoppers are now in different, a lot of shoppers stayed where they were, but there was movement between the two stores. So when you do that, you will get a decimal this time, and it happens a lot. Generally, when you're talking about something like, this situation, we're talking about customers. So what we do is we do a little approximate. So this would round to 277, and this will round to 323. So we can say, therefore, we've got approximately 277 customers or shoppers at store A, and then, of course, 323 at B. It's pretty normal to round them when you're talking about people because it doesn't make sense to talk about a portion of a person. And this one, finally, for April, we would do the same thing. That's going to be the next month. So this will be S3. We'd do T times S2 because now we've got values that look like this for the month of March, and we're transitioning those values. So what I do, instead of writing the transition matrix again, because it's already been defined many times up here, I'll write T by S2, which looks like this. Notice, though, that I don't use a rounded value. I use that unrounded one. You don't want to lose any accuracy by using something you've rounded. I've only rounded off to be able to answer that question there. So it's pretty normal to actually use this unrounded one. My decimals are getting a little bigger. You can use like a ... instead. So in terms of approximately, we've got 272 and we've got 328. What you'll notice is when you do add these together, you should get the same total number that we had earlier. So the total number of shoppers when you add them together was 600. And so you should still have 600 shoppers each time, because we're not bringing new shoppers in or taking any shoppers out of the system. There's not a store C, for example, that just pops up. So we should still have the same constant number of shoppers in the whole system. So altogether, 272 customers. There we go. Okay, so I might pause it there. You can look ahead because obviously if I just show you here, what we were doing was recursion. We did recursion when we did the finance module. So you'll see I've got a recursion relation here where we start off with our initial value, our initial state matrix. We call that S0. And to get your next matrix, so Sn plus 1, you transition or you multiply by the transition matrix. So this here, starting values is another way to describe it. Starting values in a column matrix. And this here is your next state, the next state matrix. And this is saying multiply current state, so whichever one you're up to, by T, so by your transition matrix. In our next lesson, I'm going to show you how we can use a shortcut. So say we wanted, with our shopping example, say we wanted in 12 months' time, you wouldn't want to have to find the values for February, then March, then April, then May, etc., all the way down to to say December or the following January, because that would take you a really long time to do that calculation. So next lesson, we'll look at generating a shortcut rule. As you can see, we use powers to do that. But for now, I'll stop so that you can just do some practice on, creating your transition matrices, interpreting those transition matrices, and just use recursion to actually apply a transition matrix.